Hello and welcome to workshop 6 for ENG-101 21B. And this week we're going to be dealing with integration. So we've been dealing with differentiation for the last couple of weeks, but now we're going to try to take a slightly different tack, because what we can do is what we were doing the other day. Hold on, let's get if we have a graph, oops, and have that as velocity versus time. Now what we're working on is that if we have a gradient of that graph, sorry about my drawing skills with this setup, that gradient gives us information. So remember, the gradient m is going to equal the change in velocity over the change in time using high school notation, and that's equal to acceleration. But the area under the graph, now that area itself, if we take this and work out this area here, that area is going to equal velocity times time. That's equal to distance. So the very fact that there's an area under this graph actually also gives us information, and we actually use this quite a lot. So, but wouldn't it be nice if I have a graph and if I've got a line which is described by some function, f of x equals something, wouldn't it be nice to have a formula where I stick in a value of x and then it will tell me the area? Now, wouldn't it be nice to actually have that? So if I stick in any value of x, this will tell me the area from there under that line. And that's called integration. What integration does is integration creates a formula for determining that. So if we have f of x is equal to 2x, if I want to integrate that, then I'm going to end up with if I integrate that, then I'm going to end up with 1/3 x cubed for 0 to x. Now, isn't that cool? That creates a formula for actually letting me work out. I stick in a value of x, and it will tell me what that area is for any value. Now that's cool. Now, so of course, once we've got a basic mathematical tool like this, we have to expand it. We should point out that if you do this, if you do the integral 1/3 x, and if we don't know what it is, plus c, if we then differentiate that with respect to dx, well, what do we end up with? We should end up with 3 over 3 x squared. Cancel, cancel. So if you integrate something and then differentiate it, you should end up exactly where you started. That means that integration and differentiation are opposite functions, just like multiplication, division, addition, subtraction. Now, so where do we use this stuff? We do use it all over the place. Like when I was saying with my damper system, I was running a car. It had a spring which was hooked up to a car tire. In here there was a damper, dashpot damper, or actually in my case it was an active damper. What I was getting on here, I needed a signal because I was using the force that this element here was making was equal to minus k Z dot. So this is actually equal to, force was equal to negative k times the velocity. And so I need to know what the velocity was. I tried the concept of sticking a variable resistor in here, measuring the resistance and then differentiating that. Then in the end, what I actually did was I stuck an accelerometer on the wheel and I integrated that. So force is equal to minus k, the integration of the acceleration with respect to time. And that gave me the velocity. Now, in reality, all I did was I stuck this into a block in my little program. What I had here was I had acceleration. I put in, if you ever used Simlink or VisSim, which you probably will in your engineering career, you have little blocks, you have a signal that goes in, you put it in the grader, and out of that came my velocity. Now, isn't that cool? So yeah, it is a technique that we use a lot for taking one signal, like acceleration, and over time turn it into another one, like velocity. Or velocity, if you integrate that again, I'll put another integration block in here, and then what happens is when I integrate the velocity, I get the displacement out, or I get x. Whatever. So this is one way I've personally used it, but we do use this a lot, and I have used this one already in 102. If you've got a graph, for example, pressure over volume, you can actually draw. If you have a car piston, for example, piston going up and down on a camshaft or crankshaft. Now, this piston will go up and down, depending on what these valves do. It will pressurize the whole system. So as the piston goes up, it squishes everything. It will set off the, set fire to the, it'll come back down again as the piston comes down. Then the valves open and exhaust the gas and pull in you. Now, what we actually have here is this graph. If you set this out and work it out, the area under here is the work done. If you actually go and multiply the area, pressure times volume, you end up with work or change in work. But so this is the work done as the piston expands. Is what when the petrol fires, it goes pushes down. The red is that. The blue. I'm sorry. Just a sec. I'll get rid of a couple of those lines. Let's make it a little more obvious. The green is the work that the engine has actually done. So this is the pressure. This is the pressure supplied by the engine as the piston pushes up, this line as it comes down. So the volume that's left over, which what's a good color for that? We've got green. Let's go for purple. So this volume in here, sorry, obviously don't know how to use this draw function. This volume in here is actually the work done, or the work that you can do every time that the piston engine's done. And we spend a lot of time working out what those lines and shapes look like. So that's another area. So this type of stuff turns up all over the place. It doesn't matter whether you're doing electrical or pretty much every engineering stream we do, except possibly chemistry, materials, pretty much every chemistry stream. We have to be able to know how to integrate to find areas. And if we can integrate to find areas, we can also integrate to find volumes and rather other interesting stuff. So we've got you doing some integration So remember, there's two basic types of integration that we do. There's going to be, sorry, wrong size. There's going to be integration x squared dx, where we don't know what it is, or when we integrate that, we know we're going to get something that looks like that, but we don't know exactly how far up or down that is. So that means once we do that, we're going to end up with a, oh, sorry, that's 3. We're going to have to add on a constant because there's going to be some amount we're going to have to add on. We don't know. But that gives us the general form that we can use in computer programs, MATLAB. There's also the ones where we have the distinct values. This is the one that we tend to like because then we end up with a value that we can actually work out. 1 to 0, so equals 1/3. And that gives us an exact value, as engineers we love exact values. So anyway, we've got some problems for you to try out, have some fun with those. You get now a shot in there, get one chance, and yeah, so have fun, and hopefully we'll be back in person fairly soon. Good luck.